Welcome. Here we are. This is Section 3, Characteristics of Differential Trace Routing. I'm Terry Fox. There's my information. What we're going to do is when we talk about differential traces, the problem with differential traces is that there is a common way that it is thought of in the uh, in the industry, and then there's the way that this stuff really works and really behaves. So what we're going to do is I'm going to switch over and go into hyperlinks, and I will show you some things about attenuation impedance, characteristics of the impedance, how the width, the height, dielectric constant, roughness, line separation, etc., how these things affect the various characteristics of a differential trace. So we will go through some of those things right now. So we will go through some of those things right now. Okay, this is Terry Fox, and we'll go ahead and get into specifically how these differential traces work and try to distinguish between what is believed about these versus what is reality. So here we go. What we're doing, this is one of my labs that is a 9.4 lab. It's the very simple L2 cutoff, etc. So this just happens to be the schematic portion. So this is the line sim part. I'm looking at the schematic portion of this design, and that is the actual board itself. But let's go back to the schematic itself. Now, what I've done is I've taken the generic SERDES driver, I've taken a generic SERDES receiver, I've set this thing up, and so in order to make sure that the drive point impedance here is 50 ohms, this is a very low impedance driver, as I recall, so I just simply put in two 50 ohm resistors here. At this point, I put in a 1,000 ohm resistor, this R3, and that's just so I could put probes across pin 1 and pin 2 of R3 and see exactly what the driving signal looked like. I've done the same thing over here on R4. I've got 100 ohms across there because they say, well, this is supposed to be a 100 ohms differential, therefore this should be a 100 ohm resistor. But due to the fact that there could be some common mode on these signals, I've also got termination going this way to a common point. So between VCC and ground, I've got two 10 ohm resistors. So it says that this point right in the middle is halfway between VCC and ground, or you could call it VTT, V termination voltage. And I've got 250 ohm resistors going to that center point. So if I look at a common mode signal going here, a 50 ohm roughly drive point, a 50 ohm transmission line, a 50 ohm termination to VTT, that's fine. If I look at this thing from a differential standpoint, then I've got some signal at this point, and across this 100 ohm differential line, I've also got a 100 ohm differential termination. So at this point, looking at it just sort of from a mathematical standpoint, one would think, well, this is pretty much a perfect setup. So let's go ahead and let's simulate this thing just to see what the simulation looks like. So let me get this up so it's within the window. There we go. Should see everything. So I'm looking at U1. I'm not going to worry about U1. I'm not going to worry about U2. I am going to look at across R3. So looking at R3, I want to see what is the voltage across there. So let's get R3. So I've got the voltages across R3. Actually, what I need here is I need to insert a differential probe. So I'm going to put one across R3. Okay, and where's the other one? The other one's going to be across R4. So I've got differential across R4 and a differential across R3. So what I'm seeing is I'm seeing the voltage across R3 and I'm seeing the voltage across R4. And so let's just see how that works. I'm not going to worry about R8, those things. Alright, so all I want is just the differentials, so I'm just getting rid of this other stuff. Okay, now I'll go to, eye diagram. Now it changed everything. Do I still have my probes? Bing, bing. So I've got those. I'm going to configure the eye diagram. In this case, I've got this thing running at 8 gigabits because that is, this is a DDR3 design. And with that in mind, let's go ahead and start the simulation and see what happens. Alright. So, R4, that is at the receiver. R3 is at the transmitter. Now, if you look at this, that looks like a fairly unwieldy looking signal. Now, undoubtedly this thing will work, but the question is it the best? At R4 it looks like a perfectly nice eye. If I turn on the eye mask, you can see that I have a clear eye. But the real issue with all of this is that what is the characteristic of this transmission line, and can I improve on this termination and make things look better? So the first thing I'm going to do is I'm going to take a look at this transmission line. So TL7 is connected to TL8, and if you go right mouse on it, say edit types and values, then here we go, TL7, TL8. As I click back and forth, you'll see it's these two, so these things are on the surface. They are 8 inches long. Trace width is 6 mils. Separation is 8 mils. If I look at the transmission line itself, it says that TL7 is 50 to ground, TL8 is 50 to ground, but now the differential here is 93 ohms. Well, if I was to look at the stack up here, you see that the distance from the top to the plane is 3.15. So if I was to widen out the separation here, I could probably raise this impedance. So let's say that I just made this 15, and now at 15 it says that the individual impedances are about 50.5, but now I'm up to 97. Now on the other hand, if I went down here and I said 4, then I'm down to 83. So let's go down to quite a wide spacing. Let's just call it 25. So that's a very wide spacing between these. And now I've got 50, 50, and 99.6. So let's go through and run that same simulation. Now, with this simulation, you see, let's see, got to get rid of the previous. That's what it looks like at the receiver. This is what it looks like at the transmitter. So obviously the circuit is working, but the question is, can we improve things any? So let's go back, and now if I look at the transmission line itself, let's look at the field solver view of this thing. Let's view the numerical results. So if I look at it, it says the differential impedance is about 99.6, odd mode impedance is 49.8, etc. Now, what I was after is specifically this area right here. It says optimal termination. So line to line, I've got it at 100. It says line to line in this case is closer to like 3,300. The line to ground 51.3 or 51.3. So let's try to use that information and see what we could do with it. So I'll say OK to this. So let's take this resistor and let's make it 3,300 ohms. So we've made that one larger. Now this was supposed to be about 50.9. So if you take a look at it, it says about 51.3. All right. So let's make this guy 51.3. And this guy 51.3. Okay, now let's run that simulation again. There, we've got it. Now, all I'm trying to point out is that the common wisdom, so let's look at what the signal looked like at the driver, what the signal looked like at the receiver. I argue that this is a better looking signal. The problem is that this does not look like the common wisdom of the day. Now in this case, I've got about 50.5 to ground for these two devices, and I've got them very wide apart. So we would term this as being loose coupling. It says the differential impedance is 99.6, but the resistor I've got across here is looking more like 3.3K because we're actually terminating right through these two resistors. So this is just a larger resistor. So this is now looking like 3.3K in series with about 102 ohms or so. Now let's go back and let's change and let's go from wide coupling to narrow coupling and see what happens, or loose coupling to tight coupling. So instead of being 25 mils wide, let's make this thing 6 mils, or make it a 4 mil separation. Okay, so at this point I've dropped to about 49.1 and 83 here. So let's go through and look at the at whatever is the optimal termination. So now it says line to ground is about 57.7 and line to line would be 303. So if I take the old values here and run that, now with the new separation, I'm starting to get a little bit ragged there. But if I go through and do what it told me to do, okay, 302, 57.7. All right, so let's make this 302. Make this 57.7. Make this 57.7. All right, now let's run the simulation again. That's what I had. Okay, so you see that again we're getting good looking waveforms here. And the point of all this is just to say that going through with sort of the mind-numb idea that you just terminate these things with 100 ohms, which, by the way, let's go ahead and do that. So I'll take this and remove that, take this and remove that. Now, common wisdom says that this resistor ought to be 100 ohms because this is 100 ohm differential. So with the 100 ohms in there, let's go ahead and run this again and see what we got. All right. So there we are with the 100 ohm differential and tight coupling. Now let's go back and see if we could improve on this. So we will look at this and we'll say, all right, let me look at the field solver here, view the numerical results, optimal line to line. Okay, so if we take common mode, differential Z. So if I had one resistor here, 83.5 seems to be the best one for this particular case. So let's go back and make this 83.5. Now let's run the simulation again and see what we get. Okay, so what is the point of all of this stuff? The point of all of this is that when you go through and we say, well, this is a 100 ohm differential, just going through and simply saying, well, I'm going to drop in 100 ohms here because that's what it's supposed to be, that is not the entire picture. You've got to go in and really understand what is the coupling region, and you can get that out of hyperlinks, and that will help you to understand. Now, what are the trade-offs between having wide coupling and between having tight coupling and having loose coupling? As far as how the system works, if you go to the wider coupling, you will have less crosstalk, you will have less overall loss in the system. Here we've got this setup where I'm fairly tightly coupled. Let's look at the loss on this transmission line, and I'm going to look at 1.2 dB. This is only 5 inches long, and this is also not common FR4. This is very nice stuff. So I'm going to go out to 4 gigs. So here at 4 gigahertz, the attenuation here is about 1.07 dB. Now let's go back and let's make this much wider. Now look at it, and I'll go back to 1.25, zoom in on this, and now if I get out to 4 gigahertz, still instead of being 107, I'm 1007. So in other words, going wider gave me less loss in the line, and that loss that I picked up was the basically the crosstalk loss. All right, now let's look at one other thing. If you've got surface roughness in this, and you'll have to go in and look at the characteristics in the stack-up editor to say how much surface roughness you've got, you'll find out that if you do have surface roughness, that can make a big difference. So right here at 4 gigs, we've got 10038, and if I go surface roughness and now zoom back in on this thing, now if I come out to 4 gigs, at 4 gigs, if you take into account the surface roughness, then instead of being about 1 dB at 4 gigs, it's coming out to be 1.7, or in other words, 70% greater loss. The place where that comes into play is if we go into the setup, stack up, edit, manufacturing, These are your roughness numbers that you put in, and you can specify all of that. Go to Mentor's help files on this, and you'll see how to do this. The only point in all of this is that roughness can be the elephant in the room. So if you're doing some sort of simulation and you're not looking at the roughness factor and what that has to do with your overall circuit, you can make this quite a bit more complex. Now, as far as the lab is concerned, what I would like to have you do is to go through and simply hook these things up in various ways. Why is it that I'm not being able to hook something up? Why am I not hooking things up? Okay, that is hooking up. All right. So hook these things up in various ways. Play with the values. Play with the the width, the separation. Put these things on different layers and see how it works. And the key areas that I was looking at was, one, the coupling region, where I'm looking at the trace width, I'm looking at the separation, I'm looking at the length. And if you want to look at the stack up, you can get the stack up here, or you can get the stack up right under setup. Then go over to loss. You can look at the loss numbers there. Loss amounts to the attenuation, so we either have the resistance, the resistive attenuation, or the dielectric attenuation. And so the green is the dielectric, the red is the resistive. If you go to inner layers, you'll find that your dielectric loss goes up considerably, where here it's primarily resistive loss in this particular example. But anyway, go through, work with those things, and just get some idea of how this all goes together, because you can't go through just using some sort of some brain dead ideas that you just that since it's a 100 ohm differential, you use a 100 ohm resistor here. 100 ohm resistor may or may not be the right number. The point is, what does the signal look like when you're going into your receiver? So work with those things and get them, and that is it for this part. Okay, that's the end of section 3, looking at specifically SERDES or differential trace routing. Again, take a look and run through the lab that is the simple SERDES, whatever the heck it was, and we'll move on with the next section. Thank you very much.